Hello and welcome everybody. Today in geometry we will be looking at the last two sections all condensed into one single video of chapter 9. So in this one we will be talking about two main theorems, and in fact there's going to be a little bit more condensation because I just feel like at this point we're going to take all of those kind of like a mini theorems and then just put them all into one, because I feel like that just makes more sense that way anyways. So anyhow, let's go ahead and get into it. So the first one that we're going to talk about is what happens when you have multiple transversal. And then in section 9.9, then we're going to talk about something called concurrency. So let's start with the first piece, which is going to be multiple transversal then. So this theorem right here, this is actually kind of like a 3 or 4 parts theorem put all together. And I'm just going to go ahead and prove it all into one, because in the end, that's what happens in the book anyways, because they basically took one theorem to prove the next, to prove the next, to prove the next, and then to prove the final one. And then I basically figured, okay, you know what? We can just go ahead and put them all into one instead of like making 4 different theorems then. So here's what it says. In this theorem, you have, it's actually called 9-21 and then 9-30 and then also 9-30. 0.1, so a lot of put them. So we'll just go ahead and put them all into one then. Okay, so it says that if you have 3 or more lines that are parallel to each other, such that the intercepts on the traversals are going to be congruent to each other, then all the intercepts on another transversal are going to be congruent to each other. So you can see in the picture below, what we have is we have a bunch of lines that are going to be parallel to each other. So for reference sake, you can technically take the lines that are going to be on this page, because if you notice, all the blue lines are parallel to each other. Now, what's going to happen is line 1, line 2, line 3, line 4, line 5, and so on. They're all parallel, so you can see the symbol for that. They are also all cut by a single traversal, such that all of the intersections, when you form segments between two of them, are going to be congruent. So you can see here how AB is congruent to CD, is congruent to DE, and yeah, so those are basically all of my conditions. Now, if everything falls into place as is, right, if you have a whole bunch of parallel lines such that the transversals, when you cut them, you have a whole bunch of congruent segments, then what's going to happen, according to this theorem, is that if I make another transversal somewhere out here, right, and it doesn't necessarily have to be the same as that one, doesn't have to be parallel, just some other transversal, where it cuts through all of the other lines the same way, then the conclusion is that all of these guys right here, right, all of these segments that you have, they should also be congruent to each other. So namely, if I call them like say W, X, Y, Z, and well, I guess there's one more, we'll go ahead and call it V, then that means I need to prove that these two right here are going to be congruent, and then congruent to this one, and then congruent to this one. So that is what I am trying to show. Okay, so all of those are going to be congruent to each other. Now, the way it works in the book is that they basically said, okay, let's go ahead and introduce a let's go ahead and introduce a line that's parallel to T, which is the one that's given. So by the way, I really should give this new transversal. We'll go ahead and call it T sub 1 a name. Okay, so T sub 1, I need to show all those reds are going to be congruent to each other. So what we're going to do is we're going to go ahead and introduce a line. Okay, we'll go ahead and call T sub 2 such that T sub 2 is going to be parallel to T1, or actually T, and also intersecting one of those points. So let's go ahead and say intersecting point X in this case. Okay, so if I do that, here's what that would look like. So here is a line that I'm going to introduce that's parallel to the one that I have. Okay, now this is going to be my line T sub 2. And what you'll notice is that because T and T2 are parallel to each other, then by definition, then that means that this whole piece right here, the quadrilateral that's formed by A, B, W, and X, or ABXW, that should be a parallelogram by definition. And if that's the case, then that means that by theorem, apple, which I still haven't given a better name for, says that the opposite sides are going to be congruent to each other. Okay, so then that means as a result, let me just kind of write that down. Oops, using a wrong pen over here. By definition, okay, we can say that we have ABXW is going to be a parallelogram. And then by the theorem apple, okay, then we can say that AB, the side that you can see that's given over there, is going to be congruent to the side that looks like I just created over here on the right-hand side. And I think I need to give this point over here a name where T2 and L1 is going to intersect. So AB is going to be congruent to PX. Okay, so what that means is now I can put a mark over here. In addition to that, if you notice that underneath it over here, we also have another parallelogram. In fact, technically, we have a whole bunch of parallelograms. And all of those parallelograms are congruent to each other. So hence, what's going to happen is that we basically have a whole bunch of segments that are going to be congruent to each other. But I don't need all of them. I really just need kind of like the first two. So the first one over here, this right here, PX, we know that's congruent to AB over here. So these two are going to be the same. In addition, this right here, BC, is also going to be same as this guy over here. So let me just go ahead and make that another point. We'll go ahead and call it QX over here. So you can see down here, these two marks are going to be the same thing. Now, let me go ahead and draw that picture a little bit better for you over here on the side, so it looks a little bit bigger. So here's W, here's P, here's line 1, right? And then we also have line 2 over here, right? This is supposed to be some point Q over here, according to the picture. Here's X, and then here is Y. Again, my original is that I need to prove that this side right here is going to be congruent to this side right here. As of right now, we know that this guy right here is congruent to this guy right here. Well, working with a little bit more, I noticed that we have a vertical angle in between the two. And in addition, we also have some alternate interior angles. This angle right here is congruent to this angle right here. Or technically, you can use angle on the other side over here if you want to too. But nonetheless, what that means is that those two triangles are congruent. So therefore, the pieces that we're trying to show are definitely going to be congruent to each other. And if you want, what we can do is we can go down the line and create a different parallel line over here, and different parallel line over here, and different parallel line over here. And every single time we create that parallel line to T, it's just going to be the same thing. So in conclusion, then because we have one that's congruent, then that means all of them are going to be congruent to each other then. Okay? So that is basically going to be like, all of those theorems put together. So now you don't have to memorize every single one individually, because you really only need to memorize the one that is important, which is the end. Okay, now we're going to go ahead and move into the last section, which is going to utilize that previous theorem right here. And this one is actually pretty interesting because it actually opens the door to physics, which we'll talk about in just a little bit. Okay, so this is what is known as the median concurrency theorem. Okay, so first of all, let me go ahead and read the theorem itself. It says the medians of a triangle are concurrent. And what that means is that they all intersect at a single point. So note that in the picture underneath, you'll notice that we have 3 medians because we have 3 sides in a triangle. And it says that they all intersect at a single point. So that's something that we're going to have to prove. And that point in this case, I guess in this situation, we call it P. And it turns out that according to this theorem, that this point of tangency, that's what we call it, is 2/3 of the way to each of the median. So what that means is that if you draw a median, and then from the point of tangency to the vertex A, it's going to be 2/3 of the way of the entire median. So that is to say, over here, if I can call this guy right here, let's go ahead and say, that's like 2x over here. Then that means that this guy over here is going to be x, because 2x plus x is equal to 3x, right? So one piece is going to be twice as big as the other. So hence, that's why it's like 2/3 times. So let's go ahead and see if we can kind of come up with a proof for that one, just to see where that whole idea comes from, okay? So here, first of all, let me go ahead and just go into the restate, so then that way we can set up our proof. My restate is that given triangle ABC with the midpoints of D, E, and F, respectively, I want to prove that AP, right, the length of right there, is going to be equal to 2/3 of AE, where AE is supposed to be the median. And then the same thing for BP, which is supposed to be 2/3 of BF, and also CP, which is 2/3 of CD. So we just need to kind of like, prove each one individually. Well, fortunately for us, each one of these, if you prove it once, then it's going to be the same for all the other ones because all you have to do is just rotate the triangles. So here's how we're going to prove this one, okay? We're going to start by constructing 4 other lines that are going to be parallel to BF. That contains A, F, and C, and the midpoints it's going to contain AF and C and the midpoints of AF and FC. So you can see the segment over here, which is going to be AC. What I'm going to do is I'm going to go ahead and pull out their midpoints, which is going to be F in this case. Then we're going to go further and pull out the quarter positions of those because I want the midpoints of the midpoints then. So, if you want, you can go ahead and call it some name. We can go ahead and call it X. Using the wrong pen. We can go ahead and call it X, and we can go ahead and call it Y then, okay? So here's one X, here's one Y. And what I want to do is I want to go ahead and create 4 lines total that are going to be containing these 4 points. These actually, 1, 2, 3, 4. These 4 points that I have right there. And I want them all to be parallel to BF. Now, BF is basically that median over here. Okay, so let me just kind of highlight it. So I'm going to create 4 lines that are going to be parallel to this one that goes through each one of those points. So here's what it's going to look like. The first one is going to be going through X, and it's going to look something like this. It's going to cut this way, going through X, and it goes through E, actually. And you'll actually see Y in just a little bit. Then we also have another line that goes through Y, which is parallel to BF. And guess what? It goes through D over here, believe it or not. And then the next one is going to be A. And that one, it doesn't go through anything because it doesn't touch the triangle besides A. And the last one is that it goes through C and it doesn't touch anything else because, well, it doesn't contain any part of the other triangle. Now, if you're wondering, okay, well, how do I know that those lines go through D and E? Well, it's because if you recall, these all are lines that are going to be parallel to each other, right? Because that was the condition that I set up. And so if you notice also, the way I cut it by the quarter position. So that means that this right here, AY, is congruent to YF, is congruent to FX, is congruent to XC. Hey, look at that. That's going to be our transversal. And if that's our transversal, then that means according to the previous theorem that we just went over, any other transversal that goes through these parallel lines, they should always be congruent to each other. So here you can see that BC right here, that is a transversal. So that's how I know that it goes through E because it has to cut through in 2 different spots. Then over here, if you look at AB, okay, this right here is another transversal. And it goes through those 2 lines, then that's how I know that that means that these guys right here are going to be congruent to each other. But more importantly, what I want is to focus on AP, right? I want to focus on AP to show that that's 2/3 of AE. Well, here's AP. This guy right here is congruent to this guy right here, is congruent to this guy right here. So if I call each one, like say the letter A, right? Letter A, then you can see that, 2 of these guys, right, is going to be equal to, that right there, we have 2A right there for AP, okay? And then we have 3A right there for AE. So if we put it all together, then you can see that, AP is going to be equal to 2/3 of AE then as a result. So there it is. That's going to be our proof. And like I said, for the other ones, for the other setup over here, that's going to be the same thing, but except we're going to be drawing lines that are parallel to the other medians. But, the result's still going to end up the same. Okay. Now, this point of tangency right here, not point of tangency, this point of concurrency right here, it is actually pretty special because it turns out, and this is something that, your physics teacher will hopefully, show you someday, is that this point is kind of like what is known as the center of mass, or also known as the centroid. And what that means is, like, if you can imagine that you have a piece of board that is the shape of this triangle, if you can find that center of mass or centroid, that is basically where you're going to hold it with one finger or whatever one point that you have, and you're going to be able to hold up the entire triangle. So it's basically kind of like, where everything is all balanced, and hence that's why it's called the center of mass. So, that's something to kind of think about in the near future then. So point P turns out to be what is known as the centroid. It is the center of gravity then, where everything is all balanced if you are able to kind of like draw it out. Okay, so here and here and here. So let's see if I can kind of figure out where the centroid is. First, I have the midpoint. Here I have another midpoint. Here I have another midpoint. I am going to draw the first median. So that's going to be this guy. Here I'm going to draw the other median. That's going to be this guy. And if my picture is nice enough, which is not, unfortunately, according to the theorem, I'm supposed to find, my drawing is bad, unfortunately. But, I was hoping to see if I can sketch where the centroid is, but that's obviously a bad picture. But, hopefully you'll have a better chance than I do if you're using, like, say, an actual ruler and construction and so forth. But there you go. Thank you so much for watching. I will see you guys next time and have a good one. Take care. Bye-bye.